Hello everyone. I'm Sai Venkatakrishnan, a PhD scholar in the Department of Computer Science and Engineering in IIT Madras. So this is week 8 live session for the NPTEL course Operating Systems Fundamentals. The agenda of the live sessions would be to discuss about 10 assignment questions which were offered in the previous offering of the same operating systems course on NPTEL. The main aim of this live session is to enable you to get exposed to these assignment questions pertaining to these week 8 lectures and help you to so that it will be helpful for you while solving the current assignment questions that are released in the NPTEL portal for the current offering of the same course. Okay. So if you have any queries, feel free to stop me and ask your query, or you can post it in the chat box, or you can unmute yourself and just speak up. Okay, so let's start then. Right. So question 1 is as follows. Given a set of processes P0 to P4, 5 processes are there. So they are a set of waiting processes. Under which of the following circumstances a deadlock will arise, considering the mutual exclusion, hold and wait, and the no preemption conditions are holding as well among these 5 processes. So you're given 5 processes, all are in waiting state, and in which of these 4 conditions, given 4 conditions, will a deadlock arise, assuming that already 3 conditions are holding. So any guesses which option is correct? So if you remember the 4 conditions that should hold always for a deadlock to occur is one is mutual exclusion, second is hold and wait, the third one is no preemption, and fourth one is circular wait. Okay, Arnab has answered as option C.
See with the
Sorry,
see the answer.
C is the answer. Sorry, I didn't get you, Sachin.
Yeah, C is the answer because there is a circular wait condition perhaps.
Right. Okay. So let's see one by one. Okay. So in option, so mutual exclusion, the first 3 are holding. They have given already. So circular wait we should see, and in the first one it is given P0. It is waiting for P2, and P2 is waiting for P3, which is waiting for P1. So there is no loop actually, no cycle. So this is a wrong one. In the option B, it is given like P0 is waiting for P1, which is waiting for P2, and P2 is waiting for P3. So in this case also there is no cycle. So this is also wrong. Option C, which you are telling is correct, let's see. So P0 is waiting for P2, P2 is waiting for P4, okay, and P4 is again waiting for P0, right? So there is a cycle in this wait for graph. So the circular wait condition is holding for option C. So option C is the correct answer. And option D, if you just see again, it's there is no loop would be forming. P0 waiting for P1, P1 is waiting for P3, and P3 is waiting for P4. So there is no loop. So this is also a wrong choice, right? So option C is the correct answer, since the circular wait condition is holding. So so any doubts in this question? The key point to note is you should know what the 4 conditions for the deadlock are. These 4 conditions. So then only you will be able to figure out the answer, because they have not explicitly asked you to find in which of these options there exists a loop in the wait for graph. They have just given P0 is waiting for P2, just like that. They have just in literally they have just explained the conditions, the scenarios in sentences, but they have not given the key term circular weight. So these four conditions you should know it, so that you will be able to answer this question. Okay. So any doubts in this question? If not, then we will move to the second question. Right. So, so this a minor typo. It's just like an arrow mark. Right. So the second question is as follows: consider the following resource allocation graph. So you are given this resource allocation graph, and where P1, P2, there are 5 processes P1 to P5, and the resources R1, R2, R3 are given. Now, based on this resource allocation graph, determine whether there is a deadlock or not. So, how do we find out whether there is a deadlock? Any idea? Given this graph, any idea how we can go about finding the deadlock? What conditions should hold if a deadlock has to exist?
There should not be any complete cycle, right?
Right. So there should not be any cycle. So there are, so if, so this edge from R1 to P1, so this edge means like R1 resource is allocated to P1, and this edge P5 to R1 means P5 is waiting for R1. Okay, right. So Arnab has given option A, there is no deadlock. Okay, let's see. So let's see whether there are any cycles in the first place. So let's just use a different pen. Okay. So I see one cycle over here, like from this edge is part of the cycle, this edge, and then if I just traverse, then this edge is there. Okay, and then there is this edge also, and I get this one also, and then from here again one more edge is there, so this one, and again here there is one more edge. So here it's the same node. So I get a cycle if I just traverse this part, right? So from R1 to P1, P1 to R3, R3 to P3, and then P3 to R2, R2 to P5, and then P5 to R1. So I get a complete cycle, right? So this complete cycle is there. So I have found out a cycle. So whether that's a deadlock or not. So which of the following options are correct? Do you feel? So Arnab has given option A. There is no deadlock. Any other guesses? Right. So
So there is a deadlock because cycle is forming. I mean,
right. So some of you have mentioned, Shashikant has mentioned option C. The correct answer is option B, in my opinion. Right. See, if you have gone through the lectures, when the professor is discussing about resource allocation graphs, he would have mentioned two conditions. If there is no cycle, then there is no deadlock. Okay, if there is a cycle, then you branch out. There are two conditions. One condition is if only all the resources are like single instance for all resources, and there are multiple instances of each resource, multiple instances. So if it's in a single instance, it is a deadlock. If a cycle is there, and if everything is single instance resource, so only one instance of that resource is present in the system, and the cycle is forming as part of that resource, then it's a deadlock for sure. Whereas if there are multiple instances of the resource and a cycle is forming as part of that resource, then uh, it is not always that a deadlock might be there. So deadlock may exist only. So deadlock may exist. So in the first case, if a cycle is not there, uh, there might be a case that if the cycle is not there at all, then we are sure that there is no deadlock. If there is a cycle, so I have found a cycle, but then I should see whether the resources that are involved in this deadlocks in this cycle are just having single instance in the system or they are having multiple instances. So they are having multiple instances in this case. So deadlock might exist, but we cannot tell for sure. We need further evidence. So in this case, option B is the correct answer. Why not the other options? Option C, there is a deadlock because say if you look at this graph clearly, um, you will see that I'll just erase these extra things. So we found that the cycle is over here. These are the nodes involved.
So the P4, I mean, if P4 leave the resource R1, then
Right. So P2 and P4, if these two processes, P2 and P4, if these processes, right, leave the resources, if these P2 and P4 are finished and they don't have want the resources R1, R2 and R3 still, then we can give the instance freed instances of the resources to P5, P3 and P1, right? So there is this case always. So in that case, we there is a deadlock. This thing is wrong actually, because if P2 and P4 are freed, then we can easily the cycle will be broken. Do you get my point?
yeah.
Right. So the other choice that Arnab had told, like there is no deadlock. In my case, actually both are correct answers, but it depends on. Uh, in my opinion, in my case, like I'm telling, if P2 and P4 should leave the resources, should get finished, and then the resources are freed if P2 and P4 finish. But let's if there is a case that P2 and P4 are like say some system process or um, some background tasks, and assume they are running until like your system is shutting down, so it's alive always, and assume that these two processes P2 and P4 are non-preemptible. They cannot be preempted, or they don't go into the finished state. They are always executing and they always need these resources. Then what happens is this cycle involving this cycle will always be there, because P2 and P4 are not releasing their resources. It will always be there, and we cannot for sure tell that there would be no deadlock. So that's why this answer is also wrong. So we can argue that if P2 and P4 release the resources, then there is no cycle and there is no deadlock. But it's based on the assumption that P2 and P4 release the resources, and we cannot be sure just given from this resource allocation graph. If further information is given, right, P2 will release in 5 seconds, P4 in 6 seconds, then we can argue that okay, these resources are freed and the cycle would be broken. But just from this resource allocation graph, we cannot infer much from uh, the duration or the whether it's preemptible or non-preemptible. So that's why in the lectures also, when we explain, like when professor explains that the cycle can be formed, if there is just single instance of that resource, we are for sure that deadlock is there. But if there are multiple instances, there might be a deadlock, or there may be a deadlock only. So it's not for sure. So the safe answer for this is option B. There may be a deadlock, right? Right. Yes, there may be a deadlock. That's the correct answer. So, based on the um, options given and based on the explanation given in class, option B is the safe option. Because in the lecture videos also, sir would have, I guess, taken an example similar to this or something, and he would have mentioned that if P2 finishes and P4 finishes, then the other the cycle would be broken like that. But just from the resource allocation graph, you cannot infer those information. So option B is the correct answer. The other options are wrong. So if there are multiple instances, then always we cannot infer from the graph any information. We can just say whether a deadlock is possible or not, but not for sure. So any doubts in this question? Okay, Shashikant has asked one doubt. Consider the methods used by processes P1 and P2. Okay, for accessing the critical sections whenever needed as given below. Initial values of the shared Boolean variable Boolean with S1 and S2 are randomly assigned. So method used by P1 while S1 equal to S2, critical section S1 equal to S2, method S1 not equal to S2. Shashikant, what's the question? I didn't get it. So
This is the question actually. I'm copying. I'm giving the options actually. This is the whole question, and then you have to choose the option which one is correct.
right. Let me, if there are no doubts, any doubts in this question too, actually, till now. If not, I'll just move to question 3 and then come to Shashikant's question, which he is posting it in the chat box. Is that fine?
Yeah, sure.
So, question 3, consider the following resource allocation graph. You have Pi and Ri. So, like there are P1, 5 processes, and then there are 4 resources, and determine whether there is a deadlock or not. So, this is the resource allocation graph. Uh, the first thing is you should see whether a cycle is there. So, can anyone find a cycle in this graph? Any guesses whether there's a cycle or not?
Yes, sir. There's no visible cycle actually.
Right. So Arnab and others, yeah. So there is no cycle in this graph. So the correct answer is deadlock does not exist. Option B is the correct answer. Okay. So any doubts in this question? So if there is no cycle, whether it's multiple instances or single instance, if there is no cycle, then straight away we can tell that there exists no deadlock. So any doubts in this question? Right. So let's see what Shashikant has mentioned in the chat box. So consider Okay, so we have two processes P1 and P2 for accessing their critical sections whenever. So initial values of the shared Boolean variables are randomly assigned. Okay, so one is while S1 equal to S2, and here it is while S1 not equal to S2. So this is your critical section, and then S2 equal to not of S1, S1 equal to S2. So which one of the following properties hold? Whether it's mutual exclusion but not progress. So the options are whether it is mutual exclusion and not progress, or progress and not mutual exclusion. C is neither and good. Right. This is last week related question, right, Shashikant?
Actually, I joined late, so I don't know
Right, right.
whether it was covered in the question.
So S1 and S2 are shared. So S1 and S2 is like the flag and the shared variable, right? That's what. Okay. So for mutual exclusion, right? So initial values of the shared Boolean variables are randomly assigned. So then there are four cases, right? So either in the first place, like it can be like S1 equal both are 0, or uh,
Both one and both 10 and 01.
yeah. So S2, or otherwise it will be S1 equal to 1, S2 equal to 1, right? So in so this is case 1, case 2, case 3, case 4. So for mutual exclusion, if case 1 is or case 4 is there, so 1 or 4, this P1 will enter the critical section, and finally after entering also S1 equal to S2 only. So whatever the value of S1 was there, okay, so initially S1 is equal to S2, then only it will enter, and for P2 it won't enter in case 1 and 4. And when exiting the critical section, S1 gets the value of S2 which is same as before, because initially also both are equal. Wait, so sorry. Yeah, it's oh, okay. There's a semicolon, is it? Okay. Sorry, I forgot this. Right. So,
It will be infinite loop, right?
yeah. I missed the semicolon at the end of the while loop. I thought this critical section is within the body of the loop, right? So while S1 equal to S2, it will just wait for it. So in case 1 and 4, um, P2 will enter, right? Correct me if I'm wrong. In case 1 and 4, P2 will enter because S1 not equal to S2. This will be false.
Yeah.
So in that case, P2 will enter, and once it exits the critical section, S1 will be equal to S2, and the opposite. So it's just terminated again. So S2 is not S1. Right, so at the end of this, whatever S1 was having, it will be the opposite in S2. So it will become either case 2, or it will become either case 3 at the end. Right at the end of the critical section, once it exits, S2 becomes the opposite of S1. That is nothing but not of S2 itself, you can see, right? Because this will be false. When it enters the critical section, S2 will be equal to S1, right? So in this case, S2 is not of S2. We are just negating whatever S2 has.
Well, in the right code, you should be S1 is not equal to S2. You say that S2 is not equal to S2.
S2 equal to, right? No, so like no, so initially in the question it was given S2 is not S1,
Yeah.
but when you enter the critical section, the condition for entering the critical section is S1 equal to S2 is true, right? Right? Only if this condition is true. So like if S1 equal to S2 is true, then this condition will be false. S1 not equal to S2 is false.
First and fourth case we can enter.
Yeah, first and fourth case we entered. So first and fourth case is S1 and S2 both are equal. And once it exits the critical section, this statement is executed, which is S2 equal to not of S1. So it's nothing but so whatever value is in S1 it gets negated. Since S1 and S2 both are having the same value, we can just for simplicity have it like this also. So it becomes case 2 or 3 finally. Either S1 becomes it becomes the opposite values. Both are having S1 and S2 gets the opposite values finally.
Okay.
And now P1 would be like busy waiting in this statement if it was like 1 and 4, and when once P2 exits the case becomes 2 or 3, and in that case S1 equal to S2 this will be false, and now it will enter the critical section because it is of the case 2 or 3, both are having different values. And finally when it exits it
It will
becomes
become case.
either 1 or 4,
Yeah.
right? So in this mutual exclusion is for sure guaranteed because uh, these two conditions are uh, opposite to each other, right? Either of these can only be true at any given time. Both of these cannot be true, so mutual exclusion is guaranteed. For progress, so what is progress in the first case? Progress is if this is not waiting. Say if um, okay, so say it is 1 and 4 cases there, but P2 doesn't want to enter into the loop, doesn't want to enter into critical section, right? In that case it can in that case what's the ideal scenario? P1 should be given access to enter into critical section if P2 is not willing to enter, it doesn't want to enter. But if the case is 1 or 4 and P2 doesn't want to enter, there is no way P1 gets to know gets to enter the critical section, right? It has to wait till P2 wishes to enter into the critical section, and this case 1 or 4 changes to 2 or 3, right? So progress is not guaranteed in this case.
No, I want to know. I mean, while they're saying that S1 is not equal to S2, so when they are same, P2 can enter the critical section, right?
uh, S1
P2 can enter the critical section when both are not equal, right? I
when
mean,
both are not equal, right,
so
P2
when
can
both are
enter.
equal, when both are equal.
No, so say like once P1 finishes execution, no, so say like this, so it's given like the initial values of the shared variables are randomly assigned.
No, no, I want to know that, like, there is a condition that P2 can enter in the critical section when both are equal, right?
When both are equal, P2 will enter. When both are not equal, P1 will enter. This is not equal and this is equal.
Okay.
The thing is, initially, S1 and S2 would be randomly assigned.
But when suppose P2 don't want to enter in the critical section,
Right.
and the process are equal, how can P1 enter in that case?
When P2 doesn't want to enter, how will P1 know? Right? That's your question.
No, my question is, suppose P1, the both the, I mean, we are taking the case of first and fourth, where both the conditions are equal,
Ah,
and are equal, and P2 don't want to enter the critical section.
yes.
Uh, but for P1 to enter the critical section, it must be different.
Yeah, it should be cases 2 and 3.
On that case, I mean, in that scenario, P1 can't enter the critical section.
Right. Yes, it cannot
How will,
make progress.
so how can progress be there?
How can?
How can progress be there? I mean, there will
Yeah,
be no
yeah,
progress.
progress cannot be done. That's what I'm telling. Because if P2 doesn't want to enter, there is no way P1 can enter. Given first and the first and fourth cases are true, either one of these are true,
Yeah,
right? Then P1 cannot enter. So mutual exclusion is guaranteed, but there is not progress. So the correct answer is 1. I guess Arnab mentioned in the, yeah. So option A is the correct answer. Mutual exclusion is there, but not but not progress.
yeah. It's a correct answer.
Right.
Thank you.
Yeah. Yeah. Good question, Shashikant. Thanks for sharing it. Uh, in that case, let's move to the fourth question.
Are we going to include the semaphores today?
Sorry,
Semaphores today, I mean, are you going to include semaphores?
the extra questions, is it?
No, no, I am asking, will you consider semaphore questions today?
No, no. Semaphores was last week. This is
Okay.
deadlocks mainly.
Okay.
Yeah. So question 4 is as follows. Select the incorrect statement among the following. Uh, First statement is if a system is in a safe state, then there cannot be any deadlocks. Second is if a system is in unsafe state, it implies that there exists at least one deadlock. Third statement is if a system is in an unsafe state, there may or may not be deadlocks, or option D, none of the above. So which one of the following, option A, B, C, or D, which one of the following is incorrect statement? Any guesses?
So B should not, I mean, B is not correct.
Right.
In
So,
the state, there is a possibility of a deadlock. You can't be sure for it.
right, exactly. So option B is the correct answer. So if you in the lectures you would have come across this diagram. So like this, right? So this is like this whole region is the unsafe state, and this region is the safe state, and within this is the possible deadlock state. So deadlock is just like a subset of the unsafe state. So if the process, the resource allocation or something, if it lands in an unsafe state, then there might be a possibility of deadlock, but you cannot tell it for sure. So option A and C are correct actually. Option B is incorrect statement. So for this question, option B is the correct answer. Any doubts in this question? Right. If not, then let's move to the fifth question. Given three processes P1, P2, and P3, and the process starting time, so they arrive in this following order. First P2 arrives, then P3, and then P1. So this is the execution order of the processes. and assume that all the three processes P1, P2, P3 require the same resources to execute. So to ensure safe state, which one of the following four options has to be followed? Whether P3 has to wait until P2 terminates and P2 has to wait until P1, or P1 has to wait till P2, P2 has to wait till P3, or P2 waits for P1 and P1 waits for P3, or the last option P3 waits for P1 and P1 waits for P2. So which one of the following four options should be uh, followed so that there is always the safe state? So the arrival is as follows. So like first P2 arrived and then P3 and then P1. So to ensure there is it's a safe state, which one of the following four options? Um, P2, P1, P3. Right. Just a second. There is a small mistake in this ordering. It is P2, P1 and P3. Sorry. Sorry for the typo. P2 arrived first, followed by P1 and then P3. So given this state, now can you tell which one is the correct answer? Right. So Nandan has told it's option D. So let's see. So for a safe state, what does the rule to ensure safe state? What's the rule that we have to follow? Given P1 to Pn, okay, and J less than I, process Pi, if it's waiting for some resources, then it should only depend on the then if it's waiting for some resources, right, then uh, the resources that are already available plus whatever resources that would be freed by processes that came earlier than pi, freed resources for by pj, where j is less than I, right? So only based using these resources itself, if we can allocate and execute pi, then it's in a safe state. So in this, we the question it mentions three processes are there and P2, P1 and P3. That's the arrival order, and all these three are vying for the same set of resources. So in that case, definitely there will be a contention. Since there is contending for the same resources, there might be a deadlock, but to ensure the deadlock is avoided, the safe state should always be maintained. And for safe state, the rule is the first process which came should be allowed to get hold of the resources, finish execution, and then free the resources, right? So in that case, P3 came the last, so it's the latest arrival. So P3 has to wait until P1 terminates and P1 has to wait until P2 terminates. So if this these rules are followed, then uh, there will always be the safe state which is maintained, and we can avoid deadlock scenario. So option D, as Nandan mentioned, is the correct answer. Okay. Any doubts in this question? If not, then we will move to the sixth question. Right. So the Banker's algorithm is used in which scenario? Is it used for deadlock prevention, or is it used for deadlock avoidance with resources allowing single instance, or is it used for deadlock avoidance with resources allowing multiple instances, or is it used for recovering from a deadlock?
C.
In which of the following
Sir, C. Then.
option C? Right. So Sashikant and then has mentioned option C. So that's the correct answer. Banker's algorithm is for deadlock avoidance with resources allowing multiple instances. For single instances, you can go via the graph-based method to avoid these deadlocks. But for if multiple instances are there, then the banker's algorithm is used to avoid deadlocks at all. So option C is the correct answer. So even Arnab has mentioned good. Okay. So in that case, let's move to the seventh question.
I shared a question.
Okay. So right. The enter CS and leave CS functions to implement critical section of a process are realized using test and set instruction as follows. Okay. So let me just enter here. Enter CSX and this is leave CSX. So this is x equal to 0 and then and this one is while test and set of x. Okay. In the above solution, x is a memory location associated. Okay, so x is just a memory location and it's initialized to 0. So we assume that is 0 initially. Now consider the following statements. One, uh, the above solution is deadlock free. The second statement, the solution is starvation free. Okay, starvation. Third, the processes enter the critical section in FIFO order. FIFO order. Sashikant, the fourth statement is not complete. Can you just paste it? More than, it's not complete. More than one process can enter CS at the same time. More than one process. And which of the statements is true? Okay. Enter CS.
No,
Which of the above statements is true? 1 only, 1 and 2, 2 and 3, 4 only. Okay, 1 and 2, 2 and 3. So two processes. So is there any count on the processes? No, right? Multiple processes, right? More than two,
yeah.
right? So even enter CS and leave CS, critical section of a process. Okay, using test and set instructions. Okay, so enter the CS while test and set and
There is a single process because the question states that the inter CS, I mean, and leave CS function to implement critical section of a process.
sorry, I didn't get it. Can you repeat it?
It's saying that critical section of a process. I mean, it should be single process, right?
Yeah, so the method is replicated in each process, right? So I guess that's what they mentioned.
Okay.
So if it's just a single process, then there is no need for critical section at all. You can just go ahead and
Okay. Yeah. 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 Sorry.
so test and set x equal to 0. The above routine. Okay, so deadlock free, starvation free, before order and free. More than one process can enter CS at the same time. Test and set, compare and solve. If it's test and set, what should the previous value be? Is it just testing for 1 or 0 and just setting it, right?
Yeah,
0 and 1 it's setting, right?
yeah,
Okay. It doesn't take any other parameters as in like increment it by 1 or something. No, right?
no, I
Right.
don't feel.
Test and set, right? Okay. Yeah. So, assuming that, then more than one process can enter. So option others can also just join in because I am just working it. Yeah. So this fourth statement is wrong in my opinion, right? So more than one process can enter the critical section at the same time. I don't think that's possible, right? Because so initially if it's 0, then testing and setting it, then this condition, say if P1 and P2 both are trying to enter, three processes are trying to enter, P1, P2 and P3, then P1 will enter, P2, say P2 gets the chance, so P2 is selected. So in that case it sets x equal to 1, and P1 and P3 will be still busy waiting in this thing. It will be in this while loop only. It will be busy waiting P1 and P3. And now when P2 exits, it will set x equal to 0, right? And when it sets x equal to 0, then either of P1 and P3 would get the chance to P1 and P3 would get the chance to enter the critical section again based on this test and set condition, whichever executes first, right? And also based on which one is alive at that time. Say if P3 is in waiting state and P1 gets scheduled, then P1 gets the chance to execute this while loop again when P2 leaves, and in that case P1 will gain entry into critical section. But for sure, based on this condition test and set, option 4 is false, right? Because this condition as such only 0 or 1. If it's 1 only, it will be allowed to enter. Otherwise it is false. So in that case, more than one process that can enter critical section at same time would be false. So option D is ruled out. Uh, Whether it is starvation free, I guess not. Uh, Starvation might occur, right? Because there is no guarantee that once say if P2 gets the lock, uh, the next to and P1 and P3 are in waiting condition, then
That can be infinite wait, right?
there can be infinite wait time. So say like P2 again joins the waiting queue, and once P1 exits the critical section, P2 again gets it, and then P1, then P2, and without giving a chance to P3. It depends on the scheduler and all those things, right? So starvation might occur in that case. So second option is also wrong, right? Starvation free is wrong. The solution is starvation free is wrong. So in that case, option B and C can be ruled out.
Yeah,
And the final thing is option A, that is it's deadlock free. So when will a deadlock occur? So assuming that within the critical section, the processes do not contend for the same set of resources, and Sorry, so in this case, deadlock is with respect to this x variable, right? So this is the shared variable,
Yeah.
right? So whether it is deadlock free, what do they mean by deadlock free? I
Uh,
didn't get that term.
what about the third option, FIFO order?
At least one process is running, right?
FIFO order. The processes enter the critical section in FIFO order. No, that also depends on the who sets the FIFO order, right? It depends, right? If that's what starvation free is all about now. So if it comes in the FIFO order, if it enters the critical section in FIFO order, then for sure progress is there because as in progress, as in that waiting time, we can bound it, right? But in this case, like if three processes are there and if entering the critical section, if P1 and P2 only enters, what's the guarantee that P3 will can enter into the critical section? It might be left out also, right? It might not be scheduled also. There might be a scenario, right? You don't have any queue that is maintained anywhere or something which tells okay, once P2 gets the um, uh, leaves the critical section, then P1 comes and then P3. There is no such condition, I guess. It's not given in the question.
Yeah, I mean, there is a case. So, yeah, third option will be ruled out, right?
Yeah, third option is also ruled out. So you need not worry about third option because in B and C, the second option is there, but starvation might occur in my opinion because it depends on the scheduler and all those things. And whichever comes first, whichever process executes this while test and set properly, that will gain entry into critical section, and the remaining two processes should wait, and randomly again one of those processes will execute this and pass this condition, test and set condition. So starvation might occur. So option 2 is untrue, and based on it we rule out B and C. And deadlock free, this thing just since it's MCQ for sure, like option A, I will go. But I didn't understand this term deadlock.
Hello.
What? Yeah,
Like, can I say something?
yeah,
Like,
sure.
we can say it's deadlock free because like at least one process is running, right? Like,
Okay,
at
so
least one thing is running in the background.
right. So okay. So for deadlock, the okay we can
Yeah,
put
I
it
mean,
as a deadlock or not. So based on those four conditions, we can tell, right?
yeah, I mean, the
Right.
progress is
So
happening, and
in this case, like if you just construct the wait for graph, P1 would be waiting for P2, and P3 will also be waiting for P2. So there is no cycle. So one of the conditions is broken.
Also, there is a progress, right?
Uh, no, so for deadlock, there are only four conditions. Like one is preemption, the other is hold and wait, and then circular wait. I'm just writing it over. Circular wait, and then what's the other thing? Mutual exclusion. So X is mutually exclusive, like variable only, like one process can get. So this condition is true. And preemption we are not sure. Hold and wait is also like once you get hold of this, so this is also not true, right? This is like, once you hold this, there's only one resource that is shared, assuming that the critical section does not have any other resources. We just assume this the only resource, say R1, which is this variable X, that is all the processes are contending for to enter the critical section. So the circular weight is not there because there's just one single instance, and you don't, to enter the critical section, any process does has to like wait on the process that is already there in the critical section. But the process which is there in the critical section, this P2 is, if it's there in CS already, it has got the lock, then it need not wait for any other process, right? So there is no cycle in this wait for graph. So this circular
Can't,
wait,
don't we have their infinite wait condition here? Because if the process
infinite wait.
infinite wait situation, because when the process is there and it don't change the until you don't change the set x value.
As in,
The other
okay, so as in once P2 enters its critical section, it executes forever,
yeah.
right?
So in
So
that situation, there can't be there a deadlock.
no, so that is a different scenario, right? So if the logic of P2 is so long, then there is no other way to
I mean, if you consider this particular question, and if a
yeah.
process got stuck in the in critical section forever, so in that scenario, can an other process enter the in critical section? We see because no, I mean,
No, it cannot enter in that. So if P2
in that,
cannot be preempted, and if P2 is running you according to like infinite amount of time, then the other process cannot enter.
so in such a say, there is there I mean, there will be deadlock, right?
Right, there will be a deadlock. But I just
Like
wonder whether
And
that
the
term is.
answer given first, I mean the first only. I mean A option.
we can say in that case there is no progress. If a process is like
Yeah.
running for a long time.
Yeah, so actually, like in that case, progress is the correct word as Nandan mentioned, because deadlock is something when like two processes are waiting for each other, right? And in this case, at least P2 is making progress. In a deadlock case, you when you
No,
have this cycle,
here,
both of these should not be making progress.
no, here the process are waiting for the shared variable x, right?
No, so
So
waiting is different from deadlock, right? So if it's like mutually waiting for each other, all the processes, that's deadlock. If both,
yeah, I mean, there
uh,
should be cycle. There should be a cycle.
yeah, so that's a slightly tricky way, right, of seeing. So like in a deadlock, if like say the processes that are involved in a deadlock should not be making progress at all.
They
Whereas in this case,
got stuck a particular situation. They got stuck a particular situation, right? Then will be deadlock.
sorry, I didn't get it.
I mean,
No, like
they will get stuck on a particular situation, then there will be deadlock.
no, like actually the thing is like if there are two processes, if the processes are waiting for each other, it's a
Hmm.
deadlock. Else, uh, simply they are waiting.
Yeah, it's just waiting. That's it. So if P1 is waiting for something based on P2 and P2 is waiting for P1, this is deadlock.
So
Whereas,
this can happen because if process P1 don't come out from the critical section for a long time, then obviously it will be deadlock, right?
no, no. So only if a cycle is formed, it's a deadlock. So both should be waiting for each other. In your case,
It's called busy waiting.
yeah, exactly. It's just busy waiting. So the others are just busy waiting and they are just idling away. That's it. That's not deadlock. So that's just the problem of synchronization, and it's up to your scheduler to preempt the process or or do something with it. It's not a deadlock.
Okay, okay, got it. So for deadlock, P1 should wait something from P2, and P2 wait so should
Yeah,
need something from P1. I mean,
yeah, exactly.
it should be on the both sides.
Yeah,
Then
exactly.
only can that's okay. Here we are just sharing a single variable, so both need that variable, but
Yeah, exactly.
from
It's just
input.
waiting. That's it.
Okay,
But P2 is
okay,
not waiting. It's
okay,
making progress. Yeah.
okay. Thank you. So that A option is the correct answer.
Yeah. Right.
One only.
Yeah, just check the solution, right? I'd be happy if you check it later and post it in the forum also. Yeah,
Yeah, I
if
mean,
it's
the
wrong.
answer is A. I mean, first.
Okay, okay. Okay. Yeah. Thanks, Shashikant, for sharing this question. It was interesting. So, in that case, let's move on to question 7. So, consider a set of processes P0 to P4, 5 processes, and we have 7 resources. and the allocation matrix has the size of 5 cross 7. And say if a particular allocation matrix element 3 comma 2 equal to 6, what does it imply? So out of the following four options, given this assignment in the allocation matrix, which of the following four options are correct? So the allocation matrix is 5 cross 7. So the rows actually is for, so each row implies each process, and the columns are for the resources. So that's what 5 cross 7 we can infer from that. And now allocation matrix of 3 comma 2. So assume the indexing starts from 1, right? So 1, 2, 3, 4, 5, and you have 1, 2, 3, 4, 5, 6, 7. So this is process, and this one is resources, the columns. And now 3 comma 2 is 6. So what does this mean? This means like process P3 is allocated 6 instances of resource 2. So process P3 has been allocated 6 instances of resource R2. So that's what is the correct interpretation. So option A is the correct answer. Process P3 has been allocated 6 instances of resource R2. The other options are wrong because it's not process P2, because the matrix is 5 cross 7. If it was mentioned like 7 cross 5, right, then it's just the opposite. Okay.
Sir,
And
I think that instead of R2, it should be R1.
sorry, I didn't get it.
Instead of R2, it should be R1 because resources are starting from R0, R1.
I didn't get it. Sorry.
Here it has been written that process P3 has been allocated 6 instances of resource R2,
Uh,
but I think instead of R2, it should be R1.
why?
Because here in allocation matrix it is given that 3 comma 2. So if I start indexing from 1, then 1, then comes
Yeah, yeah,
2,
yeah, yeah.
means
Yeah,
R1.
I get your doubt. So the question, in the question they have mentioned P0, P1, but the indexing what they have followed is from 1 to 3 only. So this one is for R0, this is for R1, this is for R2, and this is for P0, P1. So okay, okay. Oh, then 0. Okay, so the indexing also from 0, 1, 2. Right, right. Okay, so I made a mistake in the indexing then. Sorry. So in that case, 0, 1, 2, 3, 4, and okay, 0, 1, 2, 3, 4, 5, 6. Now is it correct?
Yes, now it's correct.
Yeah, okay. Thanks, Arnab, for pointing out the mistake. Yeah. So the indexing starts from 0 only, and right. And if it's the allocation matrix 3 comma 2, then P3 has been allocated 6 instances of resource R2. Yeah, it's a bit confusing if they don't tell the indexing and those things, right? Yeah. But in these type of MCQ questions, right, the easy way is to like consider with indexing 0 or index 1 and see whether any of the option matches then you can rule out the other options easily. So that's the advantage with these MCQ questions. So, right, so in this case, if in my previous thing, since I started from 1, based on what Arnab mentioned, it should have been R1 actually, but R1 is not present, so there was a mistake in my indexing. So if I start the indexing from 0, then it everything falls into place, and option A is the correct answer. Yeah. Sorry for the typo. Thanks, Arnab. Any doubts in this question? If not, then we'll move to the 8th question. The deadlock detection algorithm is invoked. When is it invoked? Depending on how often the deadlock occurs, or depending on how many processes are need to be aborted, or option C, arbitrarily at any point of time, or option D, both, option A and B. Any guesses?
D.
Option D.
D. D.
B.
Yeah.
Okay, so Shashikant mentions option B. Any other guesses?
D.
D. Okay, Shashikant again mentions D. Okay, so uh, okay,
No, no. I said D. I mean, it's not B. It's D.
okay, D. Okay. So right, so option D is the actually the correct answer. The reason being, the deadlock detection algorithm, if is a costly algorithm, as in you have to detect the cycles, and based on the number of nodes in the graph, if there are like n nodes in the graph, uh, resource allocation or wait for graph, then the upper bound is like O of n square, the complexity of detecting these cycles. And if the scheduler or the kernel, right, the scheduler and the kernel, if it detects cycles and wants to detect these deadlocks and detect all the cycles in the graph, then considerable chunk of time the scheduler will be detecting the cycles only. So the heuristics has to be found out properly when the detection algorithm has to be fired, because detection algorithm itself consumes lot of time. So the kernel or the OS has to maintain these heuristics. So one useful heuristics is this, depending on how often the deadlock occurs. Like say if based on some threshold, um, whether 7, if there are like 20 processes or something, then based on that there might be a deadlock. In previous scenarios there was a deadlock present, so when the total process count something crosses a specific threshold, then you can just try to detect whether any deadlock is there or not, or whether the the degree of multi-programming or the progress made by all the process together is somewhat slowing down, then that's a sign of deadlock. So all these times you can try to detect cycles and give control to the scheduler to run the detection algorithm. And option C is the wrong choice, because arbitrarily, if you without any heuristics or something, if you just blindly run the detection algorithm uh, to detect cycles, there might be cycles, but all these cycles might not result in a deadlock, because in one of the previous questions, right, a cycle is there, but if there are multiple instances of the resource, say after 2 or 3 processes finished execution in some finite amount of time in the future, say after 10 seconds, then the cycle would be broken. But since if we just run these detection algorithms at any point of time, and if it ran before those processes finish execution and free the resources, unnecessarily it will detect these cycles and it will assume that a deadlock is there. It will try to preempt the resources. So option C is wrong. And then option B, this is also like a possible heuristics that can be used, like based on the processes that need to be aborted, right? So so that's also a possible heuristic. So option D, both A and B is the correct answer. Any doubts in this question? If not, we'll move to the ninth question. How should we choose the order of process termination to recover from deadlocks? Whether based on the criteria how many processes need to be terminated, or option B, priorities of the processes to be terminated, or option C, how much longer time to completion for the process. Which one of the following options are correct? Any guesses? So the correct answer is option D actually, because all these three heuristics would be useful when we have to find out which process has to be terminated to recover from a deadlock. Say if a cycle is formed between P1, P2, P3 and P4, okay, and say if P1 is of higher priority or something, and for sure it has to be executed, and it's not wise to terminate this process. We should not do this. So the other processes should be terminated or preempted, okay. So based on the priority like that. And also say you are having multiple cycles in the same uh, graph, in the same resource allocation graph. Just removing one process will break the cycles, like say multiple cycles. Say you're having say this P1 process is part of multiple cycles in the resource allocation graph, and if you just terminate this one process P1, then it is enough to break cycle 1, cycle 2 and cycle 3. So finding this single process which breaks all these cycles and recovers from all these deadlock, then if just one process has to be terminated, right, then you go for P1. So this is also one heuristic. And also say if in another case P1, P2 and P3, this is a cycle and deadlock is there, and now if I selecting P1, but it's a case that P1 has finished around like 99% of its execution and just 1% is remaining. So in that case it doesn't make sense to terminate P1 and later again schedule process P1 and from the first start executing it, because 99% is over and remaining process P2 just assume 10% execution is over, so remaining 90% is still there. So in that case terminating either of P2 and P3 makes sense, because you don't have to waste CPU cycles in the future for executing P1 again from the starting. So all these um, heuristics A, B and C, all these things would be useful, and cluster of these heuristics would be better to when we have to choose the order of process termination to recover from deadlock and break the cycles, right? So any doubt in this question? Option D is the correct answer, all of the above, right? So if no doubts, then we'll move to the final question. Um, Hope this is visible. The question is as follows. We have to draw the wait for graph for the following resource allocation graph. So it's a simple question. Let's just draw them. Okay. So the dotted arrows mean P1 is waiting for resource R2, and this arrow means if it is allocated, right? So let's draw the wait for graph then. there will be five processes. So okay, so let's take resource R1. So in this case, R1 is allocated to P1 and P3 is waiting for R1. So if P1 releases R1, then P3 will get scheduled to, and it can use the resource R1. So P3 is waiting for P1, right? And if you take resource R2, R2 is allocated to P2, and both P4 and P1, both these processes require resource R2. And when will it get? Only if P2 frees the resource. So, so this is the case. So P1 is waiting for P2, and P4 is also waiting for P2. And let's come to resource R3. R3 is allocated to P2 and P4 is waiting for R3. So P4 is waiting for R3 and R3 is allocated to P2. So P4 is waiting for P2. So this edge is already there. And then finally for R4 resource, R4 is allocated to P5. But P2 is waiting for R4. So P2 will get the resource R4 when P5 is finished execution and it frees the resource R4 which P2 can use. So P2 waits for P5. Right. So this is the wait for graph. Uh, so P1 waits for P2. This is for resource R2, and P3 waits for P1 for resource R1. P4 waits for P2 for both the resources R2 as well as R3, and P2 waits for P5 for resource R4. So this is the wait for graph. Any doubts in this question? So there were not options. It's just like I added a question at the end. So did you understand the wait for graph construction? Uh, any doubts in this question while constructing the wait for graph? Right. Um, if there are no doubts, then that's the end of the session. Uh, yeah. Thank you so much. Uh, any other doubts you have?
No, I mean, can we have a session for process synchronization like semaphore and
Yeah. So
wait?
actually, I was waiting for your like I expected you to like post some questions on the forum. We
Okay,
discussed it right last class also because I can choose questions, but you might know those questions beforehand or something. So
okay. So I will post the questions and
yeah,
then you
if you
can check.
post it in the forum, say like at least a couple of days before, right? I'm
Okay,
I will look into it and get the answers.
okay, sure. Thank you.
Yeah. Thanks. Thanks, Sashikant. Thanks, Alnab. Thanks, Nandan. If there are no doubts, then we can end this session then. Thank you, everyone.
Okay, thanks.